All right, thank you, Nicholas. You're the only one here right now, so I am glad that you're here. So we will get started. Since it's 7 o'clock. This whole week we're talking about polynomials, and there's lots of theorems with polynomials, lots of definitions, terminology, all that kind of stuff. And some of the most important things you need to know are the remainder and factor theorems. You don't necessarily need to have the theorems themselves memorized, but you need to understand what they're telling you. So I'm going to talk about the theorems, and what they look like and what they're saying. And it's really the focus on what they're saying and what they allow you to do that's important. So just to refresh about polynomials. So we've seen polynomials when we were factoring. Polynomials are functions. If you plug in a number, you get only one number out. And so a function that is a polynomial is usually written f of x equals, and then you've got a series of terms, and the highest exponents are first, and then you count down. The key to be a polynomial is that all of your exponents are whole numbers. All of your coefficients are real numbers, so you don't have any imaginary numbers in them. And then just some terminology. That first term that has the highest exponent, that is called the leading term. The number in front is the leading coefficient, and then that highest exponent is the degree. So before we talk about the remainder theorem, we need to actually talk about the division algorithm. And so this is kind of defining what division is and remainders and what it means. So the mathy formula, let f of x and d of x be polynomials. D of x is not allowed to be 0. And the degree of this polynomial needs to be less than or equal to the degree of f of x. Then we could rewrite our original formula, our original function f of x, as this d of x times a third polynomial plus some remainder polynomial. What this is really saying is that if I have a polynomial and I divide it by another polynomial, I get a result plus some remainder. And when you write the remainder, it's a fraction because it's over whatever you try to divide by. So if you think of it in terms of when we're just dividing numbers. So if I just say I'm going to divide 36 by 5, I know that 5 does not go into 36. I can do 5 times 7, which is 35, and we have 1 left over. So this division algorithm is saying that 36 is equal to what you divided by 5 times 7 plus 1. That is what this division algorithm is saying. It's basically just kind of describing how to do division. That's why it's called an algorithm. It's just kind of weird. But the way that we usually write it in the what I have in green there is that we usually would say, well, 36 divided by 5 is 7 plus 1 over 5. Or it's 7 1/5, because you have a remainder, it doesn't divide evenly. So that's what this is saying. It's just instead of working with actual numbers, we're working with polynomials. But it's basically just saying how you do long division and then what you do with your remainder. That's all this division algorithm is doing. What's important is understanding the vocabulary so that you know what part is what. So the thing that you're starting with, your f of x, is called the dividend. What you're dividing it by is called the divisor. That's why we used d of x. Then the result of the division is called the quotient. So that's why that's q of x. And then you add on your remainder. So that's why that's r of x. So there are some questions where you'll have to identify what is the quotient, what is the remainder, what is the divisor. So you have to understand the terminology and what that means. So seeing it with actual numbers might help versus seeing it in function notation. So the division algorithm leads us into the remainder theorem. So in blue is the remainder theorem. If you have a polynomial and you divide it by something that's x minus a number, then your remainder is equal to plugging that number into the polynomial. This is a very interesting result here. It's basically saying if I take some function, some polynomial function, say 2x plus 5x minus 1, and I divide it by x minus 3, whatever the remainder that I get for that, I'll get something. I don't know what I'm going to get. I'm going to get something plus a remainder, that r of x. That remainder is usually a number. And that is the same thing as if you plugged in 3 into your function here. So if you did 2 times 3 squared plus 5 times 3 minus 1, that is going to be what your remainder is equal to. It's a really interesting property here, that the remainder from doing the division for something that's specifically x minus a number would be as if you were plugging that number into your function and getting the function value. So I've taken our division algorithm format and I've showed what that means, where your quotient q of x, this is your quotient right here, is now x minus c. We're dividing by x minus a number. And then your remainder is equal to the function at that number. So I've just kind of replaced what we had with the division algorithm with these specific things. We're dividing by x minus something or x plus something. So this is really powerful with synthetic division. So I set up my synthetic division so that I have sort of in a table form versus the book makes it look like long division. But what this is saying is that whatever number you're plugging in for your synthetic division, the remainder, the last thing you get is the function value at that point. The remainder theorem allows us to find function values for polynomials by doing synthetic division instead of plugging them into the polynomial. This is actually really nice because if you have polynomials that have really high exponents, when you're trying to evaluate them, if you have something that's like x to the 4th or x to the 5th and you're plugging in 2, you're going to have a lot of calculations on your calculator. The numbers are going to get pretty big. When you do synthetic division, the numbers usually don't get that large, and it's actually faster. So this is basically saying if you have a polynomial and you're plugging in a value for x, you can use synthetic division to get that answer rather than our normal version of plugging it in. So it's really powerful. So that's the remainder theorem. The factor theorem here. So it's sort of a corollary of the remainder theorem. So if your remainder is 0, that means it divides evenly, and thus it must be a factor. So it's just taking that remainder theorem a step further. If your remainder is 0, it divides evenly. So that means it's a factor of your original function. And this can go the other way around. So this arrow means it goes both ways. So if you have it equal to 0, then it's a factor. But it also means you can go from right to left. You have something that's a factor. That means the remainder must be 0. So we use the factor theorem to determine if something is a 0, because also if it's a 0, that remainder is 0. So the factor theorem does two things here. It tells us where the zeros are, but it also lets us factor polynomials. And again, this allows us to use synthetic division to do this. So that's the important thing you're getting from the factor theorem, is it allows us to factor polynomials using synthetic division, and it allows us to find zeros of polynomials. So let's just kind of work through this, see this with examples. I've got here, let me just label this. So this is the division algorithm that I have here. It's basically the format. And then underneath it is the remainder theorem, just the format of the remainder theorem. So we want to use the remainder theorem and division algorithm to answer the following questions. So the first one, the value of f of -6 is equal to 39 for a polynomial f of x. What can be concluded about the remainder or quotient of f of x over x minus 6? So this f of x over x plus 6, this is in the form, if we use the remainder theorem, this is basically the left side of the remainder theorem. So if you've got a fraction, that's the same thing as dividing. So this means that we have q of x plus f of c over d of x. Now, if we're dividing by x plus 6, this tells us c is a -6. So x plus 6, it's normally x minus c. So your c is basically the opposite of the sign when you've got it in this form. So if you see x plus, your c is negative. If it's x minus, your c is positive. So you're going to be having the opposite of the sign. So by dividing by x plus 6, this tells us c is -6. So that means I know here f of c, this is f of -6. And so now it says the value of f of -6 is 39. So this tells us that we have q of x plus 39 over d of x. And d is what you're dividing by. So I can also replace that by x plus 6, because that's what we divided by. So we have what can be concluded about the remainder or quotient. So we can conclude that the remainder is 39. That's what the remainder theorem is telling us, is that whatever is part of that fraction, f of c, so this is the remainder. So what we have here, they're telling us that the remainder is 39. Write that down. And then it says, well, what do you know about the quotient? Well, we don't know much about the quotient because we have something here that we can't really, we have two unknowns. We don't know f of x, we don't know q of x. So we don't really know anything about the quotient other than we know that it doesn't divide evenly because there's a remainder. So it says what can be included about the remainder or the quotient. We can't really conclude anything about the quotient, only the remainder. So that's all we can do, is that the remainder is 39. The next one, we've got given a polynomial f of x, the quotient f of x over x minus 2 has a remainder of 12. what is the value of f of 2? So this is, again, looking at our remainder theorem. And in this case, when it says the quotient f of x over x minus 2, that does not mean q of x. It's just telling us that what follows is a fraction. That's all that means there. It's not telling us that q of x equals f of x over x minus 2, because q of x has to be a polynomial, so it's not a fraction. It's just telling us it's a fraction, that's all. So it's using quotient in a different way. So just don't get confused there. So I'm going to go back to our remainder theorem again. We have f of x over x minus 2 equals q of x plus f of c over, and then that d of x, that's what you're dividing by. So that's also going to be x minus 2. So we know it has a remainder of 12. So that tells us that remainder of 12, that tells us f of c is equal to 2, or to 12, sorry. F of c is equal to 12. So that's going to be 12 up here. That's a remainder of 12. And then if you look at the beginning part, if it's x minus 2, that tells us c is equal to 2. So we put that together, and so then we know f of 2 is equal to 12, because c is equal to 2. So the question says, what is the value of f of 2? Your answer is f of 2 equals 12. So we're kind of practicing writing the format of the remainder theorem here, but the key part that that we're trying to get at here is that the remainder is a function value, and the value for where, what the x value that it matches with is related to what you're dividing by. And that's how you kind of figure out what your input value was. Are there any questions?
I came in late, so I'm not sure if I'll look back later.
Okay. This is probably the hardest example, which we're just kind of practicing the language. The other stuff I think will be easier. So we'll see if the next example kind of helps clarify for you. So here we're actually going to be using the remainder theorem. So, oops, that's supposed to say g, not f of x. This is supposed to be g of x, because I've got a value g of 2 and then the remainder one g of x. So that's supposed to be g. So g of x is negative 3x to the 5th plus 2x to the 4th plus 6x squared minus x plus 4. So evaluate g of 2. So generally when it says to evaluate by g of 2, you are plugging 2 in for x. So we have negative 3, and then instead of x to the 5th, it's 2 to the 5th plus 2 times 2 to the 4th plus 6 times 2 squared minus 2 plus 4. So we need to do a lot of calculations here to simplify this. So we have negative 3, 2 to the 5th is 32. 2 to the 4th is 16. 2 squared is 4. And then negative 2 plus 4 is 2, so I can simplify those. Then we're going to do negative 3 times 32. So it's negative 96 plus 32 plus 24 plus 2. And we get our final answer. We add all these things up. It's negative 38. So G of 2 is negative 38. When we're evaluating, you aren't doing anything on the left side. You're just plugging in numbers and then doing the stuff on the right. So the next part says determine the remainder when G of X is divided by X minus 2. This is where we use the remainder theorem. So to actually use the remainder theorem, we're going to do synthetic division. So if we're dividing by X minus 2, that means C is equal to a positive 2 because it's the opposite sign. And we do our synthetic division using 2 as our starting point. So when I set up my synthetic division, I'm just looking at the coefficients of my function G. So I start with negative 3. And then I have 2 for X to the 4th. Now I do not have an X cubed term, so I have to put a 0 because I'm missing that X cubed. Then X squared, I've got a 6. For X, it's starting with a negative 1, and then my constant is 4. So I'm just taking the coefficients from our function. We have negative 3, 2, I had a 0, then a 6, and then a negative 1, and then a 4. And then C gets written down in my lower left corner. So I set mine up slightly different. I don't set it up exactly like it looks like division. I do it like it's a table. And that first number drops down. So that first lower right is going to be a negative 3. And then we're going to multiply and add. So I'm going to be multiplying 2 times negative 3. So it's negative 6. Negative 6 plus 2 is negative 4. And then you do 2 times negative 4. So that's negative 8. Plus 0 is negative 8. 2 times negative 8 is negative 16, plus 6, negative 10. 2 times negative 10 is negative 20, minus 1 is negative 21. 2 times negative 21 is a negative 42, plus 4 gives us negative 38. The remainder is that last number that you get there. So the remainder here is negative 38. And this is where you see the connection in what the remainder theorem is telling you, because the remainder is the same thing as G of 2. You get the same number. And so the whole powerful thing here is that if you need to evaluate a function, you can either plug in that number for X, or you can do synthetic division. So I prefer doing synthetic division because I was able to do all of that in my head mentally. I didn't even need a calculator. While if I evaluate it, I needed a calculator to do my adding and all that kind of stuff. So which method, if you were trying to evaluate a function, do you prefer the top method where we're plugging in for X, or do you prefer using the remainder theorem and using synthetic division?
Well, the top one's easier to typeset.
If you're typing, yeah, the top one's easier unless you use a table. If you create a table, you can do the bottom one.
Yes.
But let's say you were doing it on hand, you know, where you don't have to worry about that. You might want to try doing it both ways and see which one's faster for you.
Yeah, I might.
Because if one of these methods is faster, then that's the one you're going to want to do, especially on a quiz. But that's what the remainder theorem is saying here, is that that remainder is the same thing as finding the function value. There are questions? Okay, let's do another example. We're only going to do these with remainder theorem, just so you can practice it. So different function, we've got g of x equals 3x to the fourth minus 22x cubed plus 51x squared minus 42x plus 8. We are only going to use the remainder theorem here just to practice it. So if we want to evaluate g of -1, that is going to tell us we're going to use c equals -1. So that value when we're setting up our synthetic division is going to be -1. So you don't switch the sign when you're doing it in function form. You only switch it and do the opposite of sign when it's in division form. So I'm going to set up my synthetic division here. We have -1, and then we've got we don't have any zeros here. We have 3, -22. I don't have any missing terms, so there's no zeros. And then the 3 gets dropped down. So I welcome you guys to do this at the same time. You know, keep going. Tell me what we're interested in. This final answer right here is that is our function value right here. This is going to be g of -1. So we want to know what is that number when you go through this. So you can go through and you could just do this all you really need is a calculator, because all you're doing is multiplying and adding. You know, I'm probably going to need my calculator here for my adding and stuff like that, but it's going to go pretty quick. So we have -1 times 3, which is -3, minus 22 is -25. -1 times -25 is 25. 25 plus 51 is 76. Multiply that by -1, we get -76. Add, we get -118, assuming that I'm doing all of my adding correctly. Multiply that by -1, you have 118 plus 8. So that's 16, should get 126 here as our final answer. And I'm going to just now do that on my calculator to verify that I haven't made any mistakes. Yep, 126. So g of -1 is equal to 126. So the next one is g of 2. So c is going to be equal to 2. So I want you guys to try this one because you're going to be practicing the synthetic division. It's going to be set up the same. We're just using a different number for what we're multiplying. So I want you guys to do this one and then give me your final answer. So you can just put that in the chat what your final answer is when you go through the synthetic division. And I'm also going to do it as well. So we've got a 0, and that matches with what I got as well. So that is our last value here. So g of 2 is equal to 0. So you're just basically on your calculator, you're taking 3 times 2 minus 22. Take that answer times 2 plus 51. Take that answer times 2 minus 42. Like you could just keep doing it in your calculator. Just the nice thing is you hit enter, then you just multiply by 2, add the next number, and you just keep doing that until you get to the end. And so that tells us the function value for g of 2 is equal to 0. Now we're going to connect this to zeros. So I've got a new function here, q of x. It's 3x cubed plus x squared minus 30x minus 10. So the first question is c equals -3 a 0 to the polynomial? So if c is a 0, when we do the synthetic division, the remainder will be 0. So to determine if it's a 0, you're going to do synthetic division on this using -3. And then if you get 0 at the end, yes. If you don't, the answer is no. So again, we're just practicing the synthetic division. So I encourage you to do that on your own and put your answer in the chat. So when we set up the synthetic division, my coefficients are 3, 1, -30, -10. And then we're using -3. Okay, so we've got agreement that c equals -3 is not a 0. I also agree because the remainder came out to be 8. Did you guys all get 8 as your remainder?
Yes.
Okay. Make sure that we don't have any, because the place where you're going to make mistakes here is with your, adding or multiplying, usually sign errors, or if you're trying to do it mentally, if you're just, messing up there. So it is not a 0 because we did not get 0 in that last spot. So we've got h of x equals x to the 4th minus 81. And the question is x minus 3 a binomial factor of h of x? So x minus 3 means that c is equal to 3. And if it's a factor, then f of c needs to be 0. So when we do the synthetic division using 3 on this, we should get 0. And if we do, it's a binomial factor. So if we do not get 0, then it's not. So this is using the factor theorem here that we are testing this. So when we set up this synthetic division, I got 1 for the x to the 4th. I do not have an x to the 3rd term. I do not have an x squared term. I do not have an x term. And then I have -81. So we have to put in a lot of zeros in our synthetic division. And then we use 3. Because if it's x minus 3, then we are checking if we use 3, is that going to give us 0? So then we just go through the synthetic division. 3 times 1 is 3 plus 0, 3. And you're going to find that you're just basically accumulating powers of 3 here because of all the zeros. And we do get 0 at the end. So you get 3. 3 times 3 is 9. 9 times 2 is 27. 27 times 3 is 81. 81 minus 81 is 0. So the nice thing is having all those zeros is it kind of makes it really nice. So the answer is yes. X minus 3 is a binomial factor. basically it's a factor. If you tried to factor x to the fourth minus 81, that is going to be one of the factors that you will get. So we're actually going to use the factor theorem essentially to factor this polynomial. So we have r of x equals 3x cubed plus 16x squared minus 5x minus 50. And if I get cut off at the end, then I will just have to finish this on the PowerPoint when I submit the PowerPoint. So we're given that -2 is a 0. So if they're telling us a 0, that's what they're telling us to use for C. So we're going to use -2 there. So I need to set up my synthetic division. I've got 3, 16, -5, -50. And then I'm going to use -2. And so now we're just going to go through and do the synthetic division here. So that gives me -6. 16 is 10. -20. Minus 5 is -25. Then I get 50. And then I get 0. We know it's a 0 because we get 0 on the end. So that's good. If you didn't get 0 at the end and they told you that it's a 0, then that's a problem. So this tells us one of our factors is going to be x plus 2. So when you write it as a factor, you do the opposite of the sign. So if it's -2, then you have x plus 2. What this also tells us is that what we have here, these other numbers are giving us the other part of the factor, because that's the quotient here. This is the Q of x from that division algorithm. So we started with an x cubed, so that means that these are x squared, and then we count down. So this tells us the other part of the factor. We get 3x squared plus 10x minus 25. So we have just factored this, knowing that -2 is a 0. We were able now to factor out an x plus 2, and then we found out what was the remainder, what was left over when we divided that out. We got the quotient, 3x squared plus 10x minus 25. But when we want to completely factor this, we now need to factor the quadratic that we have. So we still have x plus 2, but now we need to factor this quadratic. So I've got a 3x times x. And the only way to get to 25 is 5 times 5. So that's, we don't have a lot of choices here. And it's a -25. So one of these 5s need to be negative, but we need to get it to add to 10. So if I make this the first 5 negative, that my inside is going to give me a -5x. The outside is going to give me a 15x, and that's how I get that 10x. So this is my factored form of this polynomial. So you can use synthetic division to factor polynomials as long as you know a 0. You can use the synthetic division to divide that out. And then the quotient is you keep repeating this process. So if you had something that was higher than a cubic, you just keep repeating this until you get to a quadratic. And then we know how to factor quadratics. So then you use one of your methods for factoring a quadratic, like a trinomial here, to finish off your factoring. And so this allows us to factor polynomials. The hard part is just you have to know where your zeros are. And there are other theorems for that. That's we use the Descartes rule signs to help narrow down zeros. The intermediate value theorem helps narrow down zeros. And then the rational zero theorem gives us choices for zeros.